So, all we're doing is nucleophilic addition followed by elimination. We've got the general base catalyzed mechanism above. How do we know this was typically or run under basic conditions? What about that reaction looks like it's basic? You're seeing these negative charges float around. Okay? We could potentially be running under neutral conditions to see those negatives, but more than likely we're running under basic conditions. We can go through and do it under acidic conditions. That's just going to then have to be facilitated by the proton transfers to make your electrophilic enough to react. Most commonly within these sections of material, we're looking at the base catalyzed reactions, but the acid catalyzed still happens. Okay, so it still works under most cases. So both of those kind of conditions, base conditions affect our nucleophile. Acid conditions end up changing our electrophile, making the electrophile more electrophilic. But it doesn't change the substrate. It doesn't really change the nucleophile per se. Okay, it's just changing the strength of either of those two species. One of the things that we can now do is go through and look at some new substrates. And if we take a look at the column on the far right, we've got a new sequence of potential substrates. What do all those substrates have in common? They have the polar pi bond. What else do they have in common? They all have a leaving group. Okay, so we can just highlight the section that is our leaving group all the way down. Are all of those leaving groups of equal leaving group ability-ness? Okay, no. Which is going to be your best leaving group? Our top with our chloride is a very, very good leaving group. Why is it a good leaving group? It can stabilize the negative charge very well. So if we went back and looked at ranking acids and base strengths, one of the things that we looked at was the stability of those intermediates. And we could look at the negative charge, saying, is that stabilized there? Okay, that's ultimately best following under our base classification. So the first thing we would look at when looking at stability of a negative charge, the size of the atom that's holding the electrons. Chlorine is going to be a really big atom, particularly in comparison to any of those other atoms that would be holding that charge. That makes it better as a leaving group than all of the others. If we move to the next one down, we have oxygen as a leaving group. Okay, is oxygen good holding a negative charge? It's not too bad. It's small, so it's not going to be as good as, say, the chlorine, but it is very electronegative, so that could potentially stabilize that negative charge. When we move to the next selection down, you'll notice the atom is, again, oxygen. Why do we have those two species organized at different reactivities? The top one, once it leaves the structure, has resonance to stabilize it. Okay? That extra resonance effect stabilizes the negative charge, making that an even better leaving group than the one below it. If we move further down, we then move to nitrogen as our leaving group. Why is nitrogen a poorer leaving group than oxygen? It's less electronegative. It being less electronegative, it's less likely to take the electrons away from that carbon or that carbonyl bond. Okay? As we move even further down, we're back to our oxygen. Why is this oxygen now at the bottom of our list? It's already charged. For it to act as a leaving group, it has to take more electrons and it would become O-2, incredibly unstable. Okay? So this gives us an idea of what now species we can start bringing into our picture as far as our electrophiles. And we just talked through all that. I'm using the abbreviation NAE for nucleophilic addition and elimination. Okay, officially it's two separate mechanistic steps, but in that overall reaction, that's the overall reaction that's occurring. So we can refer to it by that extended name. Okay. This is not a standard way to reference the reaction. It's typically just referred to as addition eliminations. Okay. But I didn't feel like writing it all out. Okay. So some nucleophilic addition and elimination reactions are very famous, and so they've picked up a particular name for them or a particular classification. So we've got two given to you, and the textbook goes through and talks about these in relatively extensive detail. The first one is known as a trans-esterification. What happened in the course of that reaction? What's that? Interesting. So we could say that we have two more methyl groups. Okay. By doing that, you are now somehow saying that this carbon in our beginning was what was reactive. Actually, it's not even just two. It's technically three. Be three methyl groups. How can I potentially get that carbon, which for all intents and purposes is an alkane, to react? There should be kind of a big silence there. Because can you get an alkane to react? No. So it is important to notice that that is a big difference, that we now have more methyl groups. But where did those methyl groups come from? The nucleophile, our T-butoxide. When we run the course of this reaction, the T-butoxide comes in, attacks, does the addition. We break our polar pi bond. This is followed by the second step of the reaction, the reformation of our polar pi bond and the leaving group leaving, or our nucleophile, our leaving group leaving. The oxygen in our product came from where? Came from the nucleophile. It did not originally start in the structure. Okay, so we have to be careful on what bonds are being made and what bonds are being broken. Okay. Why is it more likely that we're making and breaking that oxygen-carbonyl bond as opposed to the carbon-hydrogen bonds that was initially suggested? The carbon-oxygen bond is a much more polar bond than carbon-hydrogens. Okay? That very likely means that the carbon-oxygen bond was the one involved in our reaction. Why the carbon-oxygen bond with our carbonyl and not with the carbon-oxygen methyl group? Why our left reaction? Call it A. Why that bond versus B? That's still oxygen and carbon in both cases. In A, that carbon is attached to a pi bond, making that carbon even more positive, which means we have an even more polar bond. A is the most polar bond we've got in that situation. That's most likely to be our reactive bond. B, while it is a polar bond, is not as polar as that in the case of A. It doesn't make sense to make that bond because it's a stronger bond in general. That's not going to be an easy bond to go through and make or break. Okay. So in the change of this reaction, what functional group did we start with? An ester. What functional group did we end with? An ester. So we start with an ester, we end with an ester. Oh, so that must mean nothing happened. Is it a different ester? Yeah. It's referred to as a trans-esterification because we've exchanged our ester. Right? So a trans-esterification just means that we're switching out that nucleophile / leaving group. We're changing it with a new piece. That's our transesterification. The other reaction, a saponification. What's happening in the course of a saponification reaction? What's our nucleophile? ROH, which can come in and attack our electrophilic carbon. We break the pi bond, followed by the second step of, what's that? Remaking the pi bond and kicking out our leaving group. The result is we would have ethanoic acid and, technically, our ethoxide. Right. This is an interesting reaction. Right. Would we expect this reaction to go forwards? Why not? We'll address that in a second. Okay. In our comparisons, we've always been comparing the nucleophile and our leaving group. What was the nucleophile? OH minus. What was our leaving group? O minus or an ethoxide. Which is more stable? They're about equal. Why are they about equal? Is there a difference in size? Difference in electronegativity? Resonance effects? Inductive effects? Kind of, sort of. The methyl versus a hydrogen does have a mild inductive effect, but it's very, very mild. So there's virtually no difference between this. Okay? Which would mean our reaction is going to sit in this hardcore equilibrium. We're not going to get a very high yield of our product. Okay? But already counter to that, what do we notice is our yield of our product, according to their textbook? 87%. That's a pretty high yield. What else is going on? Karsten addressed an issue on this. Ethoxide is negative, which means it can act as a base. What functional group do we just make? Carboxylic acid. What happens? It deprotonates, and really what we end up with at the end of our reaction is our alcohol and the carboxylate. Which is more stable, hydroxide or the carboxylate? The carboxylate, because of resonance. That drives this reaction forwards. And we do end up seeing a high yield. But if I want the acid, what do I have to do? Do step 2, which was add acid. Okay, that'll protonate it. Why is it referred to as a saponification reaction? Well, our initial product is drawn up here. We end up with the carboxylate salt and the alcohol. Okay. This is a very common reaction to run. In fact, most of you have encountered this product probably today. Hopefully today. It is kind of late. Do a slight change in here. What's the slight change that I made? I added a bunch of carbons to the end of it. That's it. Anybody know what that molecule is now? It's soap. Saponification is your standard reaction for making soap. You start with triglycerides. Triglycerides are a fancy name for fats, which are esters. It's called a triglyceride because there are 3 esters in a triglyceride. So if we take fats and we add a bunch of soap to it, or sorry, a bunch of base to it, what ends up happening? We made soap. Okay? That is our saponification reaction. Okay? So those are your two big kind of named reactions that come out of your nucleophilic addition and elimination reactions. So watch out for those names. They typically show up. Yes?
Does it all happen at the same time?
No. So it's not all happening at the same time, which is why I tried to color code it. I was kind of waiting to see if anybody was going to call me out on that. It is 2 steps. Okay, so in the bottom one where I still have the arrows, the red, the nucleophile attacks, breaks the pi bond. That's all 1 step. That is followed by a second step of the reformation of the pi bond. That's our purple step. Okay. And we'll look at that, I believe, on this slide. Okay. So we're going to evaluate something to do with the energetics on this. Let's pick just a standard nucleophile. Let's go through and use ethoxide. What happens in the course of our reaction? What is our leaving group in this first case? It's that OR. Okay. Since we don't know anything about its energy yet, we'll just draw it in as our general reactant energy. Our intermediate, higher or lower energy? Why is it higher? Okay, it's charged. So what we're looking at is our neutral starting material, our ester, with our now charged intermediate, should be higher in energy for our intermediate. Where should our product be? Lower than what? Lower than the intermediate. Where is it relative to our initial? It should be the same. Okay. We've got ethoxide, and our leaving group is some alkoxide. So we're looking at our product energy of coming out roughly identical to where we started. Which means if we now run our reaction, okay, we might expect an energy diagram something along those lines, which would suggest we don't really advance our reaction forwards. Okay. The reaction we just ran was a transesterification. Okay, so we started with an ester, we ended with an ester. How can I make this reaction produce a higher product yield? There's lots of answers. What's that? Add lots of reactants. Okay, that's where we got to be careful. If I just add more reactants, yes, I increase my product amount, but relative to my starting materials, my yield's the same. So I'm not improving my product yield. If I increase one of the reactants, then why would I start to produce more products? Le Chatelier's principle. Okay. So if I want to now cause this reaction to produce more products, I can increase one of my reactants, either the ethoxide or my starting ester, to help push to produce more products. What else could I do? Remove one of the products from the reaction. If I can remove one of those products, that's also going to help shift to form more product. Okay? Again, according to Le Chatelier. What else could we do? Starting to tweak our leaving group. If our leaving group was more stable, we should predict more product. So what else could I do? Oh, I'm going to regret this because now I'm going to delete everything. I could start with a different electrophile. What does that do to the energy of my electrophile? It increases it. My intermediate is still roughly the same energy. My product is still roughly the same energy. What happens to the speed of this reaction now? It goes faster because I've increased the reactivity of that electrophile. Okay. So in each of these reactions, we could go through and pick pretty much any of these starting compounds and look at how that would affect our reaction. For instance, if we jumped all the way to the very bottom, we are already at an incredibly stable species. If I then go through to look at the intermediate, it's going to be, again, roughly the same energy. My product's going to be roughly the same energy. Would I expect that reaction to occur? Okay, why not? It is thermodynamically very unfavored. You already predicted that because you said O-2 was a horrible leaving group. Okay? By changing that starting material, we can change the effective energy to get the reaction to occur. We can actually facilitate forming our reaction or not. Let's highlight this reaction, because we just looked at this one. This time around, I'm going to look at the nucleophile being hydroxide. What type of reaction would I be running? What's that? It's the soap making one. I'm taking hydroxide and I'm reacting it with an ester. If we go through and look at our reaction, we'd start with our reactants, we'd generate our intermediate, we'd end up with a product. Okay, and we said that this does not produce a lot of product. I'd have my OH and I'd have, it's an R, not an ET. Okay. And we suggested that that is not going to produce a high amount of product. We're looking at roughly the exact same energy on both of those. Okay. In fact, our acid is a little bit higher in energy than our ester. How do we know it's higher in energy than our ester? You are told to stick your hand into a solution. One of those solutions is ester. One of those is the carboxylic acid. Which one are you going to avoid sticking your hand in? The acid. Why? It's more reactive, which means higher in energy. So if we look at the way our energy diagram is now set up, would we predict this reaction to occur? No, it should never occur. We just talked about why it can occur. This is the end of just the nucleophilic addition and elimination step. Is that the end of this reaction? What else happens? We do the acid-base step. The acid-base step produces the carboxylate, which has what energy? Much lower. So our initial nucleophilic addition and elimination step gives us a disfavorable product. It can still slightly form. Once it forms, it can then go through an acid-base step to generate an irreversible product. Once I've reached that irreversible stage, according to Le Chatelier, what happens? I continue to form more of that unstable product, which then goes to make more of the stable product. And eventually what happens? All of my reactant converts to the final product. Okay. When you're asked to provide an answer for this type of reaction, more than likely what you're seeing for a reaction is our ester. You'll see step 1, OH minus, and you'll see step 2, H3O plus. I've actually already heard this question show up. And if you're drawing out your answer becomes what? The carboxylic acid. So why, when looking at a mechanism, do I have to do that deprotonation step? Because if I look at a mechanism, I've got the final product right there. Why do I have to show that deprotonation? It's part of what happens in the reaction. You have to evaluate the reactivity of each of your intermediates as they are formed in the course of the reaction. In the course of the reaction, we form the carboxylate. followed by step 2, we can now reprotonate it. Is that irritating and frustrating? Yes. You removed a hydrogen only to 2 seconds later put the hydrogen right back on, and you just spent 5 seconds drawing out all those structures. But if you're asked to provide a mechanism, you have to provide the details of what is provided in that solution. And yes, that means going through and drawing those extra steps. Thankfully, you don't have to stress about this when it comes to the final, because it's all multiple choice. You don't have to draw off those mechanistic steps. Okay? Be aware of what is happening within your reagents and what allows you to get to a final product. Just as a random fun question, what if it was written this way? What would your product now be? I heard an ROH. That is one of your products. That's true. What about the other product? Why do you have to show the carboxylate and not the carboxylic acid? There is no acid to protonate the carboxylate. You'd have to show it as the charged product. There's nothing to protonate that. Okay. If you think back to Tuesday, we looked at the protonation, deprotonation states at different pHs. This is one of those kind of systems that you have to watch out for. Okay. Be very careful what the question asks. If you encounter questions where you think it should be deprotonated and they're giving you a hard time for it and they're asking it to be protonated, send me an email. I'll go through and take a look at it and see what's going on with it. Okay. So be very careful with your protonation states with your products. Is there a question? Okay. Oops. Questions about any of that? Okay. Our overall idea, we've already talked about this a whole bunch. This slide kind of summarizes it nicely. Okay? Your reactant, your nucleophile is negative. That is your most reactive species. In your product, your leaving group is negative. That is your most reactive species. The balance between those two, or the relationship between those two, is going to determine the extent of the reaction. Does it occur? Does it not occur? Okay? So if we go through and evaluate, the leaving group being more stable than the nucleophile, what does that mean? Favors the products. If our nucleophile is more stable than our leaving group, what does that mean? It favors the reactants. Okay? You've done this kind of thing before. Now all we're doing is applying it to this overall reaction and trying to come up with some kind of predictive ability within it. And yes, we run into some weird gray areas. We just talked about the carboxylic acid one. Okay? So since that's helpful, or I think it's helpful, I'm going to draw that specifically up again. If we went through and looked at our carboxylic acid with our ester, if we just run our analysis on the relative stability of our nucleophile to our leaving group, we end up saying that they're equal, which means we don't really see a favoring for reactants or products. And yet for this reaction, we see a clear favoring for the products. Why? Secondary chemistry. Do your nucleophilic addition and elimination reaction. Draw those products and then evaluate. Should this do more chemistry? If it can do more chemistry, then this argument that we're seeing on this slide is a moot point, because that secondary chemistry could now potentially carry the reaction forward, or it could stop it altogether. Okay? This gives you the basics behind the reaction. It does not give you the answer. Make sense? You guys seem more tired than me, or this lecture is really that boring. Okay. Do we have exceptions? Yes, we just talked about one. Okay. So let's take a look at this reaction. What would our nucleophile be? the OH. What would our leaving group be? Nice attempt in trying to actually name the structure. I think it's pyrrolidine. I don't think it's actually, crap. Anybody remember the name of it? It's not pyridine. Pyridine's with the double bonds on the inside. And I think pyrrolidine is a 5-membered ring. I don't remember the name of it. So let's simplify it. Our nucleophile was negative oxygen. Our leaving group is negative nitrogen. And then we don't even have to worry about naming it. Which is more stable? Which atom is more stable? Negative oxygen, negative nitrogen. Negative oxygen, which is our nucleophile. Our nucleophile being more stable suggests which way does the reaction favor? Reactants. So we would predict this reaction to not occur to any serious extent. What's the yield of our final product? 96%. We definitely made a bad assumption here. Why is this reaction going to 96%? What's that? What's the secondary chemistry? We have a carboxylic acid and we have a negative nitrogen. A neutral amine primarily acts as a base. This is a negative nitrogen, which means it's a stupidly strong base. As soon as we do the nucleophilic addition and elimination reaction, yes, we are forming a disfavored product. That product does secondary chemistry to form what? Our carboxylate and a neutral nitrogen. So when we now go through to evaluate should this reaction occur, we need to be comparing hydroxide to the carboxylate. Why not the neutral nitrogen? Because it's neutral. The carboxylate is charged. So we compare our charge structures. Which is more stable? The carboxylate, because resonance. Okay. If we look back to our patterns on our reactions, you'll notice that our nitrogen compound is less electrophilic than our ester compound. So that would seem very counterintuitive, okay, to be able to move in that direction. We can move in that direction, okay, because of that secondary chemistry, allowing us to shift through those positions. Okay? So watch out for any functional groups that generate that secondary chemistry. You're looking at amines primarily and your carboxylic acids. So there's our free energy diagram. If we look at the relationship between those, we say our product does not form. And as we just addressed, what happens? The nitrogen picks up the hydrogen, and we end up forming a much lower energy final product. If I want the carboxylic acid as my final product, what do I have to now do? Now I add acid as a second step. Right? So if we go back to that previous, go back to that slide, you'll notice that we do have H plus added there as a second step. That was one of the first things I erased when I pulled up. Okay? So look at each of your reagents, evaluate them according to the mechanism, see what you would predict out of it, and then try to work with it. So as one more quick twist. I love me some twists. Let's look at a new reaction, except I want some of that skeleton. Actually, I want almost all of that. I'm going to change the reagent now to sodium chloride. Should I expect this reaction to occur? Heck, let's even drop in HCl. Should I expect this reaction to occur? Why not?
More stable as a nucleophile. The nucleophile is more stable.
Our chloride nucleophile is more stable than our nitrogen leaving group. There is no secondary chemistry here. So I'm evaluating the chloride with the nitrogen. Chloride is a more stable charge species. I don't expect any chemistry to really happen here, or this chemistry to happen here. Okay? Make sense?
Our O was more stable.
So in our previous case, when we had the oxygen, our oxygen, that reaction was also not favored. Why did that reaction occur? We had secondary chemistry with our acid-base reaction allowing us to form a more stable product.
Oh, so the other one you weren't adding.
In the other case, well, it's not that we weren't adding anything else. There's nothing else to add. Okay? Here, at the end of our very first nucleophilic addition elimination reaction, what do we end up with? Okay, we are comparing the nitrogen to oxide. Covering that in red was a bad idea. And when we look at that reaction, we'd say, well, the oxide is more stable than our nitride. We wouldn't predict the reaction to occur. Why did this reaction occur? You look at your products. Can the products react with each other? Yes. That internal reaction within our products takes us to the next step, which is now much more stable. If we switch this now to, instead of being the hydroxide, to say chloride, now what happens?
Oh, so chloride not react with nitrogen.
Yeah, there's no secondary chemistry that can happen at that point. The only chemistry that would be available would be to do the reverse reaction. Okay? So we just evaluate what we've got. Which is more stable, chloride or nitride? Chloride is more stable. Chloride was on the reactant side of the equation, which means this reaction doesn't occur. Okay? So that secondary chemistry that we keep referencing is ultimately coming back to the carboxylic acid formation. If you form a carboxylic acid as a potential product, you should be very careful about evaluating that system and make sure that that reaction would continue forward. Okay? We do one more? Let's stick with the chloride. Sort of. I'm going to use the acyl chloride, and I'm going to use hydroxide. Should this reaction continue forwards or not? Why should it continue forwards? Chloride is more stable than hydroxide, but we formed a carboxylic acid. Shouldn't we panic and go, oh, that's going to change everything? Why not? Chloride can't act as a base. There is no secondary chemistry. All it can do is the nucleophilic addition and elimination to get us to the carboxylic acid, and then it stops. It can't go forwards anymore. Okay? Chloride's not a strong enough base to do any more secondary chemistry. So if we change our starting material, you'll notice that what I picked in this case was a starting material that was at the very top of our activity. A starting material that's our very most electrophilic can make anything underneath it with no exceptions. The only exceptions are when we start somewhere down low and potentially try and work up. To work up, we may need special chemistry to help us through that. For instance, if I tried to start with the ester and work my way up to the chloride, we just showed that that reaction didn't work. I can't just add chloride to the reaction to get it to go upwards. Okay? That was this case, where we said chloride. I can't get that reaction to occur. I can't get to that top step because I'm going from a low step, a bottom rung, to the top rung. That reaction doesn't work. What if I want the acyl chloride? I'm telling you right now, you must make this structure from this structure. Okay. Turn the nitrogen into a better leaving group. What's your better leaving group? Remember, if we look at our ladder, our acyl chloride is the top. Okay. It is the best leaving group. Officially, bromide is technically a better one, but it's irrelevant in this case. How can I possibly get the acyl chloride from that starting material? And yes, you do know how to do this reaction. Potentially work backwards. Do you know how to get that final product from anything? How can we get a chloride attached to a structure? Substitution, good call. Substituting PCl3 isn't a bad idea. It's typically PBr3 is what you're thinking of, and PCl3 will also work. Okay, it does a substitution of what for what? An alcohol for a halide. So if I have an OH there, I can now use PCl3, which I'm not sure will work actually, might work. The standard one to go to would actually be, what was that? No, Cl2 won't do it. That's too weak of an electrophile. Cl2 is part of the name. Thionyl chloride, SOCl2. Ouch, yeah, remember, go back and review first exam, SOCl2. Okay. SOCl2 with the carboxylic acid will get us the chloride, the acyl chloride. But I don't have a carboxylic acid. How can I get the carboxylic acid? Acidic environment is going to be important. I do agree with that because we are making a carboxylic acid. So an acid is going to be important here. You guys want a really big hint?
Would it be adding some sort of other nitrogen group?
All you need to do is add KOH. Does this side look familiar at all? Let's just erase all that writing. Oops. We just did that reaction. Okay. So what I can do is react the carboxylic acid now with thionyl chloride. This will take me to my acyl chloride. Okay. Depending on what we're trying to do, we may need to convert one of our lower rungs, one of these lower down species, to an acid so that I can then advance all the way up to the top. Once I'm at the top, I now have access to everything underneath it through relatively simple chemistry. Okay? So be aware with this chemistry, you may be going backwards to go forwards. Okay? Questions? Yeah.
Can you look forward? If you just attach a hydrogen to the nitrogen,
Make it positive, does that make it a better leaving group?
So that does make it a better leaving group, but you're still then comparing chloride to that hydrogen structure. And chloride is a really, really stable leaving group. That doesn't change it. And it is kind of a weird exception because we're saying a neutral nitrogen isn't as stable as a negative chloride. It isn't. Okay? So lots of back and forth. We just went through our exception with our nitrogens. Okay? And this is actually where we get some interesting chemistry out of this. We can actually take advantage of this in what's known as the Gabriel synthesis. Okay? So here's our reaction. Take a swing at it, see what you can come up with for a final product. And then we'll talk about the individual. In fact, the first semester I started teaching 236, I was like, what the heck is this Gabriel reaction? That's crazy, that's dumb. Why would we ever do that? And I went, oh, that's actually kind of cool. After you look at it all the way. So, interesting aspects. KOH in the very first step acts as a base. What does KOH act as in the last step? A nucleophile. So we're taking the exact same species and we end up changing how it reacts in the course of the reaction. Okay? How and why can we do that? Well, in our very first step, we've got to look at the most reactive thing present. The hydrogen on our nitrogen ends up being relatively acidic. Why is it acidic? We have the potential for resonance either direction. That gets into a weird gray area. In this case, it is probably not resonance. It is actually probably due to an inductive effect, not resonance. If you're curious as to why, you can talk to me after class. Not that big of a deal to know why. Just saying that it's probably induction. The base comes in, removes the hydrogen. We now have a negatively charged nitrogen, which means that nitrogen could act as a base or a nucleophile. Okay. Well, is there anything remotely acidic left? Nope. So it can only act as a nucleophile. Well, there's nothing else in the reaction at this point, so our reaction stalls until we move to step 2. And step 2 supplies what? An electrophilic structure. We end up doing our substitution. We would then have our nitrogen with that ethyl group attached to it. And our big ring. Yes, I am that lazy. Don't give me a hard time for it. Okay. We've neutralized the nucleophile, no more electrophile. Our reaction again stalls until we add our third step, our KOH. Our OH minus can act as a good nucleophile. It can come in our first step, attack our electrophilic carbonyl carbon. Why did I have it attack the top one and not the bottom one? Oh, you're right. I should have attacked the bottom one first. It's the exact same. It does not matter which one you attack. Okay? That would be our first step. And again, I am that lazy. Second step, our pi bond comes back down and is reformed and kicks out our leaving group. So we would have in our basic pattern our OH. And as we just addressed, nitrogen negative versus oxygen negative, that is a horrible step. More than likely that reaction does not occur. But there is a secondary chemical reaction. That nitrogen acts as a base, and it just so happens right next to it there is an acid. The result, after all of that messy drawing, would then be, come on pen, dang it, Work with me. Whoops. How many people got here? Good job. How many people stopped here? Even better job. Hydroxide is still present in solution. We still have an electrophile. What happens? It does it again to the other carbonyl. The net result is that we end up with our primary amine and our carboxylate. Sorry, please say you weren't still copying that down. Okay, good. So we end up with our primary amine and now our dicarboxylate salt. Okay. So we go through an acid-base step, a substitution step, and then 2 nucleophilic addition and elimination steps, all to go ahead and produce a primary amine. Okay. And the first time I saw this, I was like, well, that was dumb. Why didn't the chemist just go through and say, well, I want a primary amine, let me do this. Take my alkyl halide electrophile and add my nucleophilic nitrogen. My nucleophilic nitrogen goes through, attacks my electrophile, kicks that out, and sure enough, what do I end up with? Primary amine. Boy, this Gabriel was a dumb guy. Until we go into lab, and what do we end up getting instead of that primary amine? A mixture of the primary amine, the secondary amine, the tertiary amine, and the quaternary amine. Your yield turns to absolute crap with the reaction of just a standard substitution. Why? That species has a carbon that can donate electrons towards the nitrogen, making that nitrogen more nucleophilic than it started. If it is more nucleophilic, what now reacts? My product reacts with leftover alkyl halide, and I do the substitution again and again and again. So I end up getting this big, massive mixture of products if I try to use an ammonia as a nucleophile, which means I don't have a way of making a primary amine. This is where Gabriel's genius comes in. We can only get the primary amine in this reaction. There is no way to form the secondary, the tertiary, or quaternary under the reaction conditions put together by Gabriel. Okay? That is the power in that reaction. Okay? It's kind of a popular reaction to ask on the ACS exam too, because you're starting with these big, massive structures. Okay? Typically what's shown, actually let's erase all that. They'd give you the starting structure of the phthalimide. You'd have your reagents in the middle, and they'd say predict the products. One of those products will be the ethanamine. The rest of them will be these big, nasty structures with the rest of all of those atoms included, and say the ethyl group off of other positions. Why? Because what are you going to do as a student? You're going to assume the biggest pieces in your reaction show up in your product. In this case, not true. Okay? So it is a very popular question to show up because you end up forming something that is relatively simple in comparison to what you started with. So watch out for that in a multiple choice question. Okay. Questions on that?
Do you have to show a third step, or will there still be leftover hydroxide from the first step?
You should show KOH in a third step. Sometimes they'll mix it all as one big, one pot kind of thing.
So, but if it's not shown, it's not incorrect?
Actually, they should be separating it out as a third step. Why? Why does it need to get shown as a third step? As opposed to just saying mixing it all together like that. What's the problem with that reaction? The OH is a good nucleophile. That would do the substitution with the alkyl halide, and you don't get the substitution happening on your phthalimide. Okay. So they should show that broken out into multiple steps. Okay. Jimmy?
So when the OH attacks in the third step,
Yep.
carbonyl, couldn't that oxygen that now is negative for a second or however long, could that pick up obviously it's not going to pick up hydrogen from the water that's in there, and water or H3O that, I guess if you're in basic conditions, you could do that.
That's what you're asking about, that species?
Yeah, instead of the, going out and kicking out nitrogen.
It's a good question, because that was actually going to be my next sequence, was talking about that. Could that negative oxygen then go pick up a hydrogen? Okay. It depends how you're going to show that hydrogen. If you're going to show that hydrogen as H+, absolutely not. Why not? Basic conditions. If you're going to say that it's picking up a hydrogen from water, sure, there's water floating around. That's valid. Does that get you anywhere useful?
I was, the way I did it, and I did that, but I added then, I just get 4 alcohol groups there now.
So what ends up happening then is if we take a look at that carbon with that hydrogen now on it, this species is particularly unstable. Why is that carbon now incredibly unhappy? 3 electronegative groups attached to it, it's going to start sucking electrons back from somebody. Okay, so it will pull them back from one of those oxygens. Okay, so it's not that that can't happen necessarily, it's just it doesn't take you anywhere stable. You're now putting yourself at a higher energy state. Okay. Would this reaction have done the same thing if instead of saying KOH, we'd written H3O+? What's the most reactive thing with H3O+? Come on, you should all be able to shout that answer out.
What? Oh, your previous
H3O+, the most reactive thing is
the
hydrogen, H+. Okay, so what should that H+ react with? A negative. Where are their electrons?
nitrogen.
The nitrogens and the oxygen. Sorry, I pluralized the wrong one there. The nitrogen and the oxygens. Where should that hydrogen go preferentially?
Nitrogen.
Why nitrogen?
Because it's less electronegative than
It's less electronegative than oxygen, so I would tend to agree with that statement, except the electrons on the nitrogen are not available. Why not? Resonance. Resonance has removed those electrons from reactivity. The nitrogen electrons are not available to act as a base. Okay? They are tied into the structure, which means the oxygen could potentially pick up the hydrogen. And we would end up forming what Jimmy was suggesting earlier, putting a positive charge on that oxygen, or sorry, putting a hydrogen on that oxygen. Now what would happen? Well, I've got water floating around and I've got that structure. Water can now act as a nucleophile and attack that polar pi bond. We do the exact same reaction. Okay? We can do our nucleophilic addition elimination reactions under basic conditions and acidic. Why do they also work under acidic? We've now got a weaker nucleophile, but we've made our electrophile more electrophilic. Okay? So you still get the same chemistry, you're just changing around the protonation states through the course of the mechanism. Kind of make sense? Okay. So, our Gabriel synthesis, super helpful, because as this is now showing, which is what we talked about, if we just take ammonia and try and react with the alkyl halide, we get a big mess of different products coming out of this. Okay. In this case, we don't see a big difference in the percent yields, but if we change the type of primary amine that we're trying to get, we can see more separation between these two types of syntheses. Okay? What's the product? Give you 30 seconds. I don't think I gave you this one today. Bonus points, write down the chapter that we talked about it. We've talked about this reaction already. There's our 30 seconds. Our reaction. Comes from chapter 10. What chemistry are we taking advantage of? It's not radical. Acid-base is our first step, but that does not explain why I can get chemistry down to that carbon. What did I just show? It's the keto-enol tautomerization. Can't forget about it. Came back, here it is again. Under keto-enol conditions, acidic catalyst, and our bromine electrophile, we can do a substitution, hydrogen for bromine, at the alpha position to a carbonyl. Okay? Kind of neat chemistry, sneaky, hidden, backwards, all sorts of fun stuff. What happened when we run this reaction under basic conditions? So now I'm saying, real quick switch. Actually, I can just erase everything. Now, instead of it being H+, it is now OH-. What do I get as a product? Give you 10 seconds on this one. Still officially 5 seconds. Same thing gets you 1/4 of the points. There's half your points. 3/4, full credit. Pauli substitution occurs. Okay, why? As soon as we do one substitution, our product is now more acidic than what we started with. We end up pushing further for more keto-enol tautomerization. Okay? So, Pauli substitution was a big, big issue. What happens if I change the substrate now? Don't look at any of that. Stop looking. To that guy. Basic conditions and my halogen. Okay. Basic conditions, I get the Pauli substitution again. This is now a very special case, though. As we addressed earlier, we now have a carbon with 3 electronegative elements attached to it. What is that carbon now screaming for? Electrons. So it starts to say, F this, I'm leaving. For it to leave, though, something must help push it off. Is there something else that could supply electrons to our electrophilic carbonyl carbon? Say more of that hydroxide. This is another fun reaction because the hydroxide acts initially as a base to go through and do our substitution. It then goes through and acts as a nucleophile in a nucleophilic addition-elimination reaction. The end result, whoops, stop that, is our now carboxylic acid with our carbon with its 3 bromines and that now lone pair of electrons. It's now doing okay, except we have a negative carbon. What's an issue with negative carbons? It does not stabilize the negative charge very well, and what does it end up doing? It grabs the hydrogen from our carboxylic acid, and we would do what we've been calling our secondary chemistry. We would end at that product, which is then followed by step 2, the addition of acid, which goes through and finalizes, protonates it, and takes us to our carboxylic acid. Okay. This reaction is relatively famous because the chemistry that occurs here is very, very, very quick. It is so quick that we can use it as a classification test, which we'll end up talking about potentially next week, if not in 2 weeks in lab. Okay. That chemistry happens so rapidly that we can use it to identify something about our starting compound. For this reaction to occur, I needed to have a carbon with 3 hydrogens on it so that I could substitute those hydrogens for bromines. And those hydrogens needed to be acidic. Well, why are they acidic? They are alpha to a carbonyl. Okay. If that condition is set, if I have a methyl group alpha to a carbonyl, I now have the conditions to go through and produce the carboxylic acid. The reason this becomes important is not so much for the synthesis of the carboxylic acid, but really the other product. This species is not soluble in water environments, which means if I run this reaction, that thing precipitates or starts to cause the solution to go cloudy. If I see that cloudy solution, that means what I started with had a methyl alpha to a carbonyl. I now know some information about my starting material. How this gets asked as an ACS question: which of the following compounds gives the yellow solid HCl3 when mixed with iodine and sodium hydroxide? It is the exact same thing as we just looked at up here, except instead of it being bromine, it's now I2. And instead of it being CBr3, it is now CI3. That compound, HCI3, is iodoform. This reaction is known as the iodoform classification test. What does it test for? Methyl ketones. So what you would do is look at your answer choices and say which of those is a methyl ketone. You've already seen this question, and I guarantee you will see it again on the next exam. Okay? And you saw it in the context of nomenclature on top of just knowing the chemistry. Okay? Be aware of it. You need to know it. It's going to show up. And I'm done. I apologize. I talked too much.